In this video, I'm going to go over section 1.1 from your textbook, which is called Inductive versus Deductive Reasoning. This section, really this entire chapter, is about logic. So let's look at a couple of definitions before we look at some examples. The definition of logic is that logic is the science of correct reasoning. Well, let's talk about what reasoning is. Reasoning is where you draw inferences or conclusions from known or assumed facts. So in some of these problems, they will give you what's called a syllogism. We'll talk about what a syllogism is in just a minute. And they will tell you some facts that you're allowed to assume. So we're going to draw conclusions from those facts that they let us assume. We're going to look at two different types of reasoning in this section. The first type of reasoning is called deductive reasoning, and the second type of reasoning is called inductive reasoning. So we're going to talk a little bit more about deductive reasoning first. Once you have defined and analyzed a problem, it may fall into a known category of problems so that you can apply a common solution. This type of logic is known as deductive reasoning, and this is the important part. This is what you should definitely write down. Deductive reasoning is the application of a general statement to a specific instance. So they're taking general statements and applying them to specific instances. One of the most famous examples of deductive reasoning comes from Aristotle. For Aristotle, logic was the necessary tool for any inquiry, and the syllogism was the sequence followed by all logical thought. So he's saying that you use syllogisms whenever you are using logical thought. A syllogism is an argument composed of two statements or premises. There are a major premise and a minor premise, followed by a conclusion. So here you can see an example. This is what all or most of your examples will look like on the homework. You will be given a major premise and a minor premise and a conclusion. And then you'll have to determine whether it's valid or invalid. We'll talk about that in a minute. Or you may be asked to tell whether it's deductive reasoning or inductive reasoning. So this is one of Aristotle's best known syllogisms. It says, our major premise is that all men are mortal. Our minor premise is that Socrates is a man. So if we're assuming that these two statements are true, all men are mortal, Socrates is a man, so therefore we can draw the conclusion that Socrates is mortal. Alright, so we're taking general statements like all men are mortal and we're applying them to a specific instance of this person, Socrates. Now let's talk about valid or invalid. Don't confuse valid and invalid with true and false, because those aren't the same things. So it says, for any given set of premises, if the conclusion of an argument is guaranteed, that is, it's inescapable in all instances, then the argument is valid. Alright, so you're going to be given statements or premises that you have to work from. You may not agree with these premises. You may not think that they're true. But you have to, for this problem, assume that they're true. And if the conclusion of that argument using those premises is guaranteed, then that argument is considered valid. If the conclusion is not guaranteed, so that is, you could think of at least one example in which it doesn't follow, then the argument is considered invalid. So let's look at an example. This comes from your section 1.1 homework, and this is number 1 from the homework. It says, construct a Venn diagram to determine the validity of the given argument. So here's our major and minor premises and then our conclusion. Our major premise is that all pesticides are harmful to the environment. Our minor premise is that no fertilizer is a pesticide. And our conclusion is that no fertilizer is harmful to the environment. Alright, so let me teach you how to construct a Venn diagram of this syllogism. You always start with the ending part of your major premise. That's going to be your big circle in your Venn diagram. So draw yourself a big circle and label that harmful to the environment. Alright, so inside of this circle, goes anything that's harmful to the environment. So you could put in here pollution, littering, cigarettes, anything that you think is harmful to the environment. Now, our minor premise says no fertilizer, or excuse me, we haven't finished yet. Inside of here, we need to put pesticides because they're telling us that all pesticides are harmful to the environment. So let's make ourselves a little circle inside of this big circle, and this will be our pesticides. So pesticides are harmful to the environment. So that's one example of something that's harmful to the environment. Now, we can move on to our minor premise. It says no fertilizer is a pesticide. Okay, so what that tells us is that fertilizers do not belong in that circle that says pesticides. So where do we put it? Do we put it in the harmful to the environment? Do we put it outside? Is it not harmful to the environment? We don't have enough information to determine where it goes. So I'm just putting it on the border here. Now we have to determine if this is valid or invalid. So our conclusion, no fertilizer is harmful to the environment. Well, we don't really have enough information to draw that conclusion. So therefore, this is an invalid argument. So since we don't have enough information to determine where fertilizers belong, do they belong inside of the circle that says harmful to the environment? Are they outside of that circle? Since we don't have enough information to determine that, this is considered an invalid argument. Now let's look at another example. This is another example from your homework, section 1.1 homework number 3. It says construct a Venn diagram to determine the validity of the given argument. Our major premise is that all poets are loners. Our minor premise is that all loners are taxi drivers. And our conclusion is all poets are taxi drivers. Now, once again, do not confuse valid with true. We're not saying that this is true, we're just saying that this argument is valid. Okay, so, or we're trying to determine if it's valid or not. So let's go through our steps of creating our Venn diagram. Alright, so once again, we're using the ending part of our major premise. So our big circle is just loners. Alright, so our big circle is all the people that are loners. So you could put every person in here who you consider to be a loner. And we're told that all poets are loners. Alright, so we put a little circle inside of loners, and we label that poets. Alright, so all poets belong in the big circle of loners. Now our next statement, or next premise, our minor premise, is that all loners are taxi drivers. Okay, so what I did is I just went ahead and added in under loners. These are the same thing, all loners are taxi drivers. So this is the big circle, the blue circle is all loners who are also taxi drivers. And it says, therefore, all poets are taxi drivers. So is that valid given this argument? Yes. So poets belongs in this big circle of loners and taxi drivers. So that would tell us that all poets must also be taxi drivers. So this is valid. Now once again, this may not be true, but it is valid according to the premises that we were given. Next, we need to talk about inductive reasoning. This is our second type of reasoning that we're going to talk about in this section. So it says, the conclusion of a valid deductive argument, remember deductive goes from general statements to specific instances, that conclusion, if it's a valid deductive argument, that conclusion is guaranteed. But with inductive reasoning, there are arguments that are in which the conclusion is not guaranteed, even if the premises are true. So let's look at an example. So in this example, we're going to go from specific instances to general statements. That's what inductive reasoning is. So it says, Jose sneezed after petting Franco's cat. That's our major premise. And then our minor premise is that Jose also sneezed after he petted or he pets Paulette's cat. And our conclusion, our general statement, is that Jose is allergic to cats. Now, let's consider this. Let's consider whether or not that conclusion would be guaranteed. No, this conclusion is not guaranteed. It could just so happen that maybe Jose has a cold at the time. Maybe he's allergic to something else. Our conclusion is not guaranteed. Now, that doesn't mean that inductive reasoning is bad. We all use inductive reasoning every day. Reasoning of this type, where you go from a specific case to a general statement, is called inductive reasoning. And although it may seem to follow, and it may in fact be true, the conclusion of an inductive argument is never guaranteed. So that is sort of opposite of deductive reasoning, where if you had true premises and your argument was valid, then your conclusion is always guaranteed. But with inductive reasoning, it's not always guaranteed. It's never guaranteed. So let's look at an example of inductive reasoning. A lot of the examples of inductive reasoning on the homework deal with sequences or patterns. So this example says, what is the next number in the sequence? 1, 8, 15, 22, 29. So if you want to pause the video and take a second to identify the pattern and then come up with the next number in the sequence, you can stop now. So what's the pattern that you're observing here? We're going from 1 to 8, 8 to 15, 15 to 22, and then 22 to 29. To me, the pattern looks like you're adding 7. So if we were to add 7 to 29, that's going to tell us that the next number in the sequence should be 36. This is an example of inductive reasoning, and the conclusion is not guaranteed. We're not 100% sure that the next number in the sequence should be 36. There could be some other pattern at work that we don't recognize. So without further information, we can only use inductive reasoning to give one or more possible answers. So 36 is one possible answer. We're going to come back to some more examples of inductive reasoning, but in this example, all we have to do is classify a given argument as inductive or deductive. So before we actually do that, let's review. Just to review, a deductive argument is where you start with general statements and you draw specific conclusions. And inductive is where you go from specific statements to general conclusions. So general to specific is deductive, specific to general is inductive. This is definitely something you would want to write down, something you want to have maybe like on a little note card to help you study. Alright, so let's go back to our problem. Let's look at part A. It says, my television set did not work 2 nights ago. And then our second premise is that my television set did not work last night. So those are specific instances or specific statements. And then their conclusion is that my television set is broken. That's a general statement. So if you're going from specific to general, that's inductive reasoning. Let's look at part B. Part B says, or the major premise is that all electronic devices give their owners grief. My television set is an electronic device. Those are general statements. And the conclusion is that my television set gives me grief. Since I'm talking about my television set, that's a specific statement. So if we're going from general to specific, that's deductive reasoning. Now here are the more fun problems. These are the pattern problems. It says fill in the blanks with what are most likely to be the next letters. This is straight off of your homework. You should have something that looks, if not exactly the same, it should look very similar. Alright, so we have J, F, M-A blank blank. Alright, so take a second, pause the video. Now this one's kind of a hard one. JFMA. So what I'll see a lot of students do is they like write out the whole alphabet and try to label the numbers, but that's not going to help you. What I would do is you want to think of something that we use all the time. In fact, there are 12 of them all together. If you were to list out every one in this pattern, there are 12 of them. So maybe that'll give you a hint. This is the months of the year. So January, February, March, April. So given that information, our next two letters should be January, February, March, April, May, June. So M and J. So once again, this is inductive reasoning. We're not guaranteed that this is the pattern that they were looking for, but it's most likely what the pattern was. Here we have homework problem number 10 from section 1.1. It says find the general rule or pattern used to assign the given letter to the given word, and then fill in the blank with what letter fits the pattern. So we have circle C, square S, trapezoid T, octagon O, and hexagon. This one's pretty easy. Usually people get this one pretty fast. It's the first letter of the word. So circle starts with C, square starts with S, and so on. So our letter that we should fill in should be H for hexagon. And then our last example, this is number 14 from your homework. This should be the last problem on your homework assignment for this section. It says, once again, find the general rule or pattern used to assign the given letter to the given word. Fill in the blank with the letter that fits the pattern. Banana Y, strawberry R, asparagus G, eggplant P, and lime. Alright, so banana Y, strawberry R, asparagus G, eggplant P. If you haven't figured it out yet, take a second, pause the video. Alright, these are the colors of the food, or the first letter of that color. Alright, so bananas are yellow, strawberries are red, asparagus is green, eggplant is purple, limes are green. Alright, so if you have any trouble with any of the other patterns, don't stress over them. Just send me an email and I can help you figure out what the pattern is.